it's time to start the party. So happy Thursday, folks. Another lovely Iowa Thursday in February. It will end at some point, just not yet. We just have to hang on. June is our reward for making it through the winter, where everyone else is sweating to death. June is lovely. So is May, actually, for that matter, but we're not there yet. I say this because my husband is on a working trip in Puerto Rico right now, and he sent me a picture of the beach where it's 85 degrees. Thanks, honey. Yeah, I needed to see that. I'm sorry?
Do you tell him his stuff will be outside when he gets home waiting for him?
Yeah. Like, enjoy the ice. I didn't salt it. Good luck. That's your job, pal. No, it should be gone by then, I would think, but who knows? So we finished the binary example and the binary section of the lecture. We're ready to start Too Legit to Quit, as I call it, which is, no, Siri, I'm not talking to you. Okay. She keeps interrupting me. I don't understand. You would think that Do Not Disturb applies to my watch, too, but apparently not. Anywho, we're ready to start categorical data. And do you remember what I promised you at the end of class last time? You don't? Thank you for your honesty. Does anyone else? I promise that you already know how to do this. It's just an order of complexity higher, but it's all the same skills. That's what I promised. So I have an example of an ordinal analysis and a nominal analysis when we're predicting outcomes that are categories of things, where they're not really numbers, even if they're stored in the data set as numbers. So I'm picking up on slide 24, but I also have open example 2b, which we will need as well, using the same data set, but different types of models. So there's three main categories here of link functions that are used for categorical data. There's probably more, but these are like the main ones that you'll see. And once you get used to these, then you can easily adapt to pick up new ones as you need. I will tell you that the words that people use vary across disciplines, so I will try to give you synonyms by which you might otherwise recognize these names. So categorical data or categorical outcomes is sort of the biggest category. Within that is ordinal or nominal, based on whether the categories have a natural ordering to them or not. By the way, in item response theory models, so when we have latent traits predicting these same exact types of outcomes, these are called polytomous. So that's another word that you may hear in this idea. In each of these cases, if we have C possible categories in terms of the number of outcome choices, then we need C-1 binary, a term I'm inventing, submodels. So it's one overall model, but it has different pieces to it, whose job is to predict different aspects of the outcomes. And the link functions, then, these models are in charge of dictating whether this model is ordinal, nominal, or some combination in between. In most cases, these are going to be logit link functions, although you can also do these in probit flavor or complementary log-log flavor or the other asymmetric links that we had. So here are the three main categories and the corresponding link functions. If you have an ordinal outcome that you're predicting, and it's definitely ordered and no one's going to disagree with you about that. So Likert scale type answers, anything where it's like, how often do you do this? Never, sometimes, frequently, always, those kinds of questions where it's intended to convey differences in amount, but doing so in a qualitative distinction. We're going to use something called a cumulative logit link. If you have ordered categories that might be debatable, so for instance, if you have a problem that requires two distinct kinds of abilities to solve it correctly, you might have like someone who got neither aspect of the problem, somebody who got one aspect but not the other, somebody who got the other aspect but not the first one, or they got both, where like the middle two, you're not sure which should be higher, those kinds of situations. Those are known as partial credit models in IRT. The link function that you can use that doesn't assume ordering for all of them is called adjacent category logit. This one, for every reason, is not used very much, even though to me it's the most intuitive. I don't know why that is, but it is what it is. The third option then is for not ordered categories. So kinds where there is no ordering, there's no intended ordering. That is known by a couple different names. The link function is called a generalized logit. It is also known as multinomial regression, so like in Stata, that's what it's called. I would call it a nominal model, that's what it's also called in IRT, or baseline category logit. But the key idea here is that all of these things work with logits. Thus, the basis of my joke, long-standing too logit to quit. So I have to put this in here as a disclaimer because I listen to a podcast some of my friends do, Quantitude, where they had an episode about these models and they named the episode Too Legit to Quit. And I was like, that is my joke. So I took it personally and put it on here. But here's the YouTube link. You can enjoy this video after class. It starts about 8 minutes into a 15-minute music video. So at the time this video was made in like 91 or so, it was the most expensive music video in the history of the world. It's filled with all of the celebrities who were popular back then. So it's kind of a trip down memory lane. But anyway, if you're like, what the hell is she talking about? Just ignore me. It's fine. We're just going to work with logits. Deal? Deal. Aye. So here's the first one. This one is very, very common. It is also potentially the most confusing. Agreed? Yes. There's many sources of confusion, and I'm going to try to remove those sources as best I can, but I'm just putting it out there. This can be confusing. So this model has a bunch of names. It's for ordinal. That's the bottom line. Hang on to that word. It's known as cumulative logit in terms of what the link function does. Proportional odds is another synonym for this because that is the assumption the model makes, but it's testable. It is also known in IRT world as a graded response model. And here are all the different ways that we can estimate it, and I will show you how to do this in Stata and in R, and I have SAS code that does it as well inside the download folder for example 2b. The key idea here is that we are estimating C-1 submodels for C categories. So if I have 3 answer choices, I need 2 submodels. If I have 4 answer choices, I need 3, and so on. Every submodel is using all of the data at once. But each submodel is predicting a different transition point between your categories. So the fact that all the data is being used is what makes it cumulative. So if I had 4 answer choices that corresponded to 0, 1, 2, 3, I'm using numbers here, but this would apply to anything that's like never, sometimes, often, always, or strongly disagree, agree, like usually there's words involved, but I'm using the numbers just to sort of keep it generic and applicable to everything. So if I were to fit a model for 4 answer choices that are ordered, the first submodel would divide up the 4 choices into a binary 0 on one side or 1, 2, or 3 on the other. The second submodel would divide it up into the next transition point, 0, 1 versus 2, 3, and then 0, 1 versus 3, 0, 1, 2 versus 3. So each of these then you can think about as a binary logistic regression per submodel, where we have what the 0 would be, and I'm doing air quotes, is the lower set of choices, and the 1 is the higher set of choices. So the red corresponds to the 0, the blue corresponds to the 1 in each of these. So your job, what makes this confusing, is keeping track of exactly what y is for any given parameter, because y could be the logit of picking something above 0, above 1, or above 2. So we will end up with 3 different intercepts, one that corresponds to the logit of the probability of predicting the blue part in these models. So here's an example then of what that would look like in notation. If I'm predicting the blue, which is my preference, predicting up like usual, submodel 1 would be the logit of the probability of a response greater than 0. Submodel 2 would be the logit of the probability of a response greater than 1 and then greater than 2. So you can write it either way. You can describe what it's greater than or what it's less than, but the way that I've done it is consistent with what blue is in the slides here. So then each of these, if this is an empty model, meaning no predictors, would only have a fixed intercept, and I am using the second subscript here to indicate which submodel this is from. So I've got beta 01, beta 02, and 03. They're all O because they're all intercepts. But is it the intercept for submodel 1, 2, or 3 is the question, because you're going to get 3 of them on your output. And no, they will not be neatly labeled. That would be too fun. Each of these, though, because an intercept is a predicted outcome, we can reverse logit, inverse link, unlogit, back translate, whatever phrase you want to use, into probability, e to the logit over 1 plus e to the logit. So the empty model will tell us directly what is the probability of answering greater than 0, greater than 1, or greater than 2. That means to figure out what the probabilities are for the ones in the middle, we have to subtract between the two. So that's why this is known as an indirect model as opposed to a direct model for the ones that are in the middle. So this is my wording. I don't know that anyone else uses this wording, but submodel is the best way that I can think of to explain it. Because overall, this is all happening at the same time in one model and one analysis, but these are different equations to describe different parts of the outcome variable. Okay, with me so far? Maybe, yes, cool, all right. So then this idea right here seems like it should be straightforward, but some programs, instead of giving you the logit of the higher category as an intercept, actually most programs that I've found default to giving you the red instead. The word for that is called a threshold. I hate thresholds with a fiery passion, but the world has decided to use them for reasons that are unclear to me. Here's the trick. Because logits are symmetric, if the output gives you a threshold instead of an intercept, you can always get your intercept back. If I tell you that the logit of the probability of a 1 is 2, then what does the logit of the probability of a 0 have to be? Minus 2. So let me go back like 2 weeks to remind you why that is, because this is an important point. Slide 8. The link between logits and probabilities here. Logits are symmetric about 0. So if I know that the probability of a 1 corresponds to a logit of 2, I know that the probability of a 0 corresponds to negative 2. So if you end up with thresholds against your will, take the minus sign off and it's fixed, or add it, as it were. That's one source of confusion as to what is the intercept of your model. Is it in threshold form or is it in intercept form? I am going to teach you how to phrase everything in intercepts as much as humanly possible, because that makes it easier and internally consistent with how the equation works to create an outcome. So back to slide 26 here. So once you've figured out whether you're predicting the red or the blue, and hopefully it's the blue like normal, then this is how we would get back to what the probability is for any of the intermediate categories. And again, it's an order of operations problem. So if I know what the probability is of a 1, 2, or 3 instead of 0, and then I have my next submodel that tells me what the probability is of a 2 or a 3, then to figure out, to isolate what the probability of a 1 is, I have to subtract. So the probability of 1, 2, or 3 minus 2 or 3 tells me what the probability of a 1 must be. So these models do tell you, at the end of the day, what is the probability, conditional on your predictors, of answering in each category, but they do it in this weird, convoluted way. Fortunately, all of our programs will spit that out for us if we know how to ask. So you don't have to do the math to go between the equations. It will do it for you. But it's important to understand what the equations are doing so you know how to interpret the parameters. So the slopes of the model then, here's the proportional odds part as it is known. In these models, they default to having a different intercept per submodel, either a different intercept or different threshold. So you will get a different starting point for your prediction based on whether you're predicting, say, an answer greater than 0, 1, or 2. So that's the beta 0, 1, 2, 3 in this first column here. But the rest of the model by default in most packages, and a lot of packages don't even have a choice to change it, is that the slopes are the same, regardless of what you're predicting. So beta 1, if I'm talking in slope language, a slope is always the change in the outcome for a 1 unit change in x, right? Beta 1 is the same symbol in all three equations because it's constrained to be the same number in these models. So you're saying the change in the outcome for a 1 unit change in x doesn't care which outcome you're predicting. x1 has the same impact whether you're predicting a logit better than 0, better than 1, or better than 2. Now that's a constraint that may work in some cases, but we should certainly check to make sure that that's the case. Because otherwise it seems weird to make this big deal about how we got to treat it as ordinal, but then ignore how the slopes relate to the outcome and the ordinality of that. So these models default to acknowledging that it's ordinal in the intercepts only, not in the slopes. But I'm going to teach you how to do what's known as partial proportional odds or non-proportional odds and actually test whether these slopes are different across submodels. Then you can figure out which ones can be the same and which ones need to be different for any given data problem. Okay. So those of you who are nodding with this, have you had this experience in trying to figure this out? Do you want to share any stories?
It was really hard. And I may or may not have cried.
Okay,
But
tears, frustration.
eventually it makes sense once you know how to do it. You know, like, I was figuring it out a lot on my own for my master's, and so it was a lot of trial and error for me, and I think that's what was hard. But, like, hopefully it'll be easier for everybody else since we're going through all of this.
I can't guarantee it will be easier, but what I can guarantee is that I can be the tour guide through the hard. Because the process, honestly, that I went through, so in this unit, the R code for it, the package that I'm using is, like, it's unnecessarily complicated, and I searched for something easier. And everything that I found that was easier either didn't have the option to test proportional odds, to let these slopes be different from each other across submodels, or it insisted on giving me thresholds and wouldn't allow me to have intercepts. And both of those were deal breakers. So I had to wade through like all the same stuff in terms of figuring out exactly what the software was doing. And the only reason that I knew what it was doing is because I had a baseline that I understood to compare it against. So this is another case in which the first thing we're going to do is estimate an empty model, not because it's useful, but because then it will tell us what the hell is happening in the model. That's step one, is figuring out what are your submodels, what is y, and is it going up or is it going down? Okay, question?
Just like as a clarifying question, so is B01 through 3, like the bolded betas, those are the intercepts for each of the submodels, is that right?
They are.
Okay.
So we would talk about beta 01 as the expected logit of an answer greater than 0 when x1 and x2 are 0. And this is the expected logit of an answer greater than 1 or an answer greater than 3. But from there, it's just an answer. Like the slopes don't care what they're predicting because they're all constrained to be the same, which is weird and testable, I think. But it turns out to be more difficult to test it. So if you're in a situation where you have like all of these slopes want to be different, that is the point at which you might consider switching to a nominal model instead, which is a dummy coding type of approach. Yeah, that's a couple slides from now. But basically, then you designate one outcome as your reference, and you predict the logit of answering each other possibility relative to that one. That may make sense even in ordinal data if you have a very complicated model where these slopes are unequal sometimes and equal other times, and it gets to be too much of a headache trying to figure it out. Nominal is more straightforward in that sense because you know exactly what you're predicting. Nothing is constrained to be the same across submodels, but it also has way more parameters because nothing is constrained to be equal across submodels as well. So each of these link functions then, backing up, there's 3 main kinds. We're only talking about the first one. Each of these uses the same conditional distribution. So remember the 3 parts of a generalized model, right? We got link function. What are link functions for again? We talked about this last time. What problem do they solve? Starts with a B. Boundaries. Link functions are to keep predicted outcomes within boundaries. We have the regular part of the model that works the same once you predict the link. What's that called? Linear predictor. That's where the slopes go, fixed and random effects, more broadly construed. And then the third part. The third part is what kind of distribution does it make sense for your outcome to have based on the values that it could possibly have. A normal distribution only makes sense for outcomes that are plausibly continuous and reasonably symmetric after you predict them with stuff. Well, the distribution we're going to use for all three of these models, whether it's ordinal or nominal or something in between, is called multinomial. And it's basically Bernoulli for more answer choices. It's the probability of that answer if that's what you said. The end. There's no variance, there's no skewness, there's no nothing. We just have to know what three of the probabilities are if there's four, and we can figure out the fourth one because they got to sum to 1. So C minus 1 probabilities. That's the distribution that we have here. So the reason that I don't like the term multinomial regression is because multinomial is actually the distribution, not the link. So multinomial doesn't tell me if this is an ordinal model or a nominal model and what my submodels best be, because it's all using the same distribution under the hood. So here are the other two links then that multinomial would go with. Adjacent category logit or partial credit is the one, like I said, I like. It's 3 submodels still, but it's not cumulative. Each submodel focuses only on 2 of the possibilities. And you would predict the logit of getting a 1 instead of 0, or a 2 instead of 1, or a 3 instead of 2. Easy. Yes?
How is that different from regular logit? Couldn't you set up just a regular logit with 0 versus 1, and have just 3 separate models?
Yes. It is not different if you make the slopes all different. So if you literally carved up your outcome into 3 binary variables like this, and you fit a separate model for each, that should give you the same conclusions as if you fit this model so long as you allowed the slopes to differ. But this is another model in which by default they're constrained to be the same. So the slope doesn't care if you're predicting 3 instead of 2, 2 instead of 1, or 1 instead of 0. You'd think it would, but it doesn't. So yeah, that is another sort of, if it gets too ugly, chopping things into pieces is a reasonable alternative in many cases. Ding, ding. All right. The doorbell sort of worked like a Law and Order gavel for that one. Ding, ding. I made a point. Bing, ding. I like this one. No one uses it. I think part of the reason why this is less common is because you can run into problems for categories that are infrequent. So if you don't have a lot of people who said 3, then this last model is not going to be estimated well. That's still true in the other one for the ends, but it's better for the ones in the middle. And then nominal, baseline category is the other one. This one is also relatively more straightforward. This one is the same in IRT as well. It's called nominal in that case. There you designate one of your outcomes as a reference. You can pick which one. And you compute the logit of answering something else relative to that reference outcome. So it's like dummy coding, but on the outcome side. In nominal models, unlike the others, it starts with an assumption that everything needs to differ across submodels. Intercepts, slopes, everything. I have a note here from your textbook. The Stata book has a section on this that I hadn't seen before, so I thought I'd throw it in here. It assumes independence of irrelevant alternatives, that basically the model works even if you were to remove one of the choices in one of the submodels. That doesn't, it doesn't seem like it is testable, but they provide a way to do so. So that's one other thing to keep in mind when you're talking about nominal. But I feel like these two are more straightforward than cumulative logit, but cumulative logit is what the world has decided to use. So I'm going with the grain on that one. Okay, do you want to see an example of first of ordinal and then nominal? Fair? It was a rhetorical question. Can we pretend to be excited? Yay! All right. See, I'm a giant nerd. I actually am excited, but people are not randomly assigned to their jobs, so perhaps that had something to do with it. I'm a giant nerd who thinks this stuff is cool, and therefore this is what I have chosen to do for my day. But even if you're not a giant nerd like me, do you know why it's important that you learn this? 2 reasons. Do better work on the things you did want to do here, and 2, get paid. If you understand these models, someone will pay you, either as a side hustle or as a job. I know a number of people who trained in PhDs to go do something. They ended up in a career that was adjacent to that because of their stat skills. So this stuff is hard to figure out on your own. That's the reality. But that's my job. If this were easy to figure out and all you needed was Google University, then this would all be a waste of time. Okay, so I have a lot of descriptions of the data and caveats here about why I'm using what packages I'm using. This is example 2b. This is the same data set that we used for the first example, but now we're predicting the 3 category of how much they want to apply to graduate school, where I've decided on the labels. 0 means I'm not going to apply, 1 is eh, and 2 is yes, I'm very likely to apply to graduate school. We're looking at undergraduate GPA, whether one of their parents has a graduate degree, and whether they went to a private university as our 3 predictors, the same things. So I'm going to show you 3 sets of models here, starting with a standard proportional odds model. So this is the default, where you get a separate intercept across submodels, but the slope's all the same. Then we will look at what happens if we allow the slopes to be different. Which ones want to be different? How would you figure that out? How would you let some be different and some be the same? And then the last set of models is the nominal version, where we don't pretend like this is ordered and we just predict the logit of something relative to a reference, which is a reasonable alternative for these types of data as well. In terms of the software, there is a Stata package that everyone uses called OLogit, which stands for ordinal logit, I think. I'm assuming that's what it stands for. But it only gives thresholds. It does not give intercepts. So I went to Google University and I asked, how do I get OLogit with intercepts instead? And I found a package called GoLogit2 that someone had written. So in Stata, just like in R, people write packages and you can use them. So if you go search GoLogit2, a window will pop up and you can download the package and install it. So this works regardless of whether you have an installation of Stata on your own machine or whether you're on the virtual desktop. I tried and it will let you install it on the virtual machine. So you should all be able to use this. So this one is, I think, intended to be GOLogit and then 2 because it's the second version of it. But when I read this, do you know what it says? GoLogit, GoLogit, GoLogit. See, someone else is excited about these models too. It's GoLogit time. 2, because you know what's better than GoLogit 1? 2 of them. Absolutely. In R, however, the GLM package, which is the generalized modeling in base R, does not have non-proportional odds and it spits out thresholds. So I went looking for something else and I found something called VGLM, which is inside of a ginormous package called VGAM, whose documentation leaves a lot to be desired. So that's what I ended up with last year, and then when I was complaining about it, all of my students who love R tried to help me by finding other packages that would work better. So I played with those to see if they were better, but then I ultimately came to the conclusion that they weren't. The other ones that I investigated was the CLM function within the ordinal package and POLR, I don't know what that stands for, maybe proportional odds logistic regression. Let's go with that maybe. That seems plausible from the mass package. These ones either only gave me thresholds or didn't have non-proportional odds or spit out something that was hella confusing because it switched the direction of the slopes and the intercepts. And I was like, nope. So I'm going to stick with VGLM. Yes?
I know we covered this a minute ago, but can you go over the difference between the threshold and the intercept again? And how do you know which one you have?
That is literally the first thing I'm going to show you.
Okay. All right.
Yep. Yep. I absolutely will, because you do have to know that to be able to interpret what your intercepts mean. And then the ability to make sure that your slopes are always predicting the higher response rather than the lower response, which was another thing that I struggled with across these packages. They were inconsistent in what they gave you. So yes, that is the first thing that we're going to figure out is what do we have? What are the submodels predicting and which way are they going? Absolutely. Okay, yes, so that's all the stuff that's relevant here. I have a note about using SAS and stuff. We're still using likelihood ratio test results as well for everything that's going to be multiple parameter tests. Oh, I know one more thing I had to say. So the downside of VGLM and why I went searching for other stuff is because it provides different standard errors than the other packages do. The long story of it is that it uses a different source of how the standard errors are computed from the maximum likelihood iteration process. It uses something called expected information rather than observed, and expected is worse than observed. So the caveat is that some of these standard errors are going to be a little bit too small relative to what they would be in a different package. So if you have very little data, like if you have a very small sample, this will matter more. As a result of this difference, I'm not going to ask for any standard errors on your next homework, and I'm not going to ask for any T or F tests that would involve standard errors. So I've already figured out a way to like work around this problem. So the estimates will match, the standard errors will be a little bit off, and the p-values will be off a little bit in R. They're the same in Stata and SAS though. Okay, so here's our answer key for figuring out what the hell is going on. This little frequency table right here. So this is Stata output for tabulate command. I have prop table that would have given me the same thing in R. And so here are my three choices. So I have 55% of my respondents said I am not applying to graduate school. 35% said, maybe. And only 10% said they are very likely. This is how we can figure out what is happening in the submodels, which of these probabilities that we get back, and how they're added together. I have the labels stuck in the output here just for our reference, but in everything that follows, it's going to be 0, 1, or 2. The reason for that is that you have to change the code if you add labels to these things, and I didn't want to make code that wouldn't be transferable. So it's 0, 1, or 2 in this example. So here's the empty model that we're going to end up with, and then I'll show you how I knew that this was what we're going to end up with. So first, terminology. This idea of the logit as the log of the odds of the probability of a 1. Remember that from last time? Do I need my conductor stick? I can just do my hands, right? The logit is the log of the odds of the probability of a 1. That is still true. We are redefining what 1 is, and we're redefining what 0 is. So in the first submodel, a 1, the part of the odds that's in the numerator here for probability, is the probability of a 1 or a 2 relative to a 0. So in the first submodel, the 1 is a response greater than 0, and the 0 is the 0. In the second submodel, the 1 is an answer of 2, and the 0 is an answer of 0 or 1. So rather than saying 0 or 1, I'm going to say higher or lower. Are we cool with that? So these models are going to predict the logit of the probability of the upper choice instead of the lower choice. I'm abbreviating that with a simpler notation in what follows, the logit of apply greater than 0 or the logit of apply greater than 1. So apply 3 is the name of our outcome variable today because we've got 3 categories in it. So the empty model then, if we understand what's happening, empty model has an intercept, so 2 beta zeros, 1 for the submodel labeled 0, 1 for the submodel labeled 1. I went with 0 and 1 because greater than 0, greater than 1. I wanted these to match. If I translate that predicted logit into a predicted probability, these numbers are what are going to appear on our output momentarily. E to the logit over 1 plus e to the logit is a probability of 0.45 for the first submodel. If I go up to my answer key here, where does 0.45 come from? A 1 and a 2 put together. The first submodel is predicting the logit of the probability of a response greater than not. So 1 minus the intercept from the first model will give me the probability of a responsive not instead. If I wanted to figure out what the probability of, what the logit was for the lower response, if I know that my predicted logit is minus 0.2, a logit of 0.2 would give me the opposite. It would give me the probability of the 0 instead. Thresholds versus intercepts. The intercept is the logit of the higher choice. A threshold is the logit of the lower choice. Threshold times minus 1 is intercept. Threshold times minus 1 is intercept, not just relevant for figuring out what the hell your software is doing in this class, but those of you who might take SEM with me, structural equation models, guess what? They give you thresholds when you predict categorical outcomes. Of course they do. But knowing that threshold times minus 1 is an intercept will help you get back to familiar territory. Okay, so putting it together. The first submodel is going to give us the logit of the probability of the upper choice, which is 1 and 2 put together. 35% plus 10% gives me the 45%. The second submodel is going to give me the logit of the upper choice, which in that case is answering 2 directly instead of 0 or 1. So the logit for that is minus 2.2, which converts into a probability of 0.1. So these probabilities and being able to map them back onto the data is how I know what I'm getting back. So these are the numbers that we're going to see. I will show you the code and the output where they come from in just a second. Okay, any of that you need me to say again? No, we're good? Well, guess what? It's going to be on YouTube. You can hear it as many times as you want. But I know how it is when you lose the thread of something early in the process and then the rest of it's gone. I don't want that to happen. This stuff is hard. Okay, so how did I figure out that that's what I have here? And what does it look like? Stata in R. And normally in my classes where I teach multiple packages, I have the code in the different programs in only one set of output. But in this, the output is different enough that I have to show both to help people who are trying to learn to do this in Stata or R. So I forgive the redundancy. But unfortunately, in order to be clear in both packages, I have to go over both. And there's enough people who want to use both that I feel like it's a good use of time. Okay, so we're going to use GoLogit2 in Stata. It's not blue because it's a user-defined thing. I have code in the online files that go with this that help you find it and download it and install it. So empty model, outcome only. Here's the piece of it. So far it looks exactly like Logit or OLogit. 400 observations. Likelihood chi-square is 0, negative 0 in fact. That's because this is the empty model, and this is the test against the empty model. The coefficients table is giving me a row entitled 0 and a row entitled 1. They're both labeled underscore const, which is Stata for this is my intercept. The first coefficient is the minus 0.2. That corresponds to the intercept for y greater than 0. That's my first submodel. So this is the logit of the probability of answering 1 or 2 instead of 0. Lumped together, 1 or 2. The second submodel, intercept, is minus 2.2. That is the logit of the probability of answering 2 instead of 0 or 1. Here's the -2 log likelihood that you'll need for your homework. Here's some more fit statistics about this model relative to others yet to be examined. And then margins, my best friend. Can you just tell me what the probability is of each? Sure I can. Answer 1, answer 2, answer 3, 0.5535.1. So it does all of the mental gymnastics for you to figure out what the probability is of each answer, which I really appreciate. Otherwise, what we would have to do to figure out that the middle category is a probability of 0.35 is to say, well, the probability of 1 or 2 is 0.45. And if the probability of a 2 is 0.1, then the probability of a 1 must be the difference, which is 0.35. That's what it's doing for you. Okay. With me so far? So here's what we would get out of O-logit instead, the more common stated routine for this. It gives you something called cut 1 and cut 2, which is your first clue that this is not an intercept. Cut point, maybe? I'm not sure what cut means.
I think that's what it is.
Cut point,
It's like
yeah. And so note these are the same numbers with the minus sign removed. These are thresholds. So rather than predicting the logit of the higher category, which is intercept, these are the logits of the lower category for each submodel. So this is the threshold telling us the probability of a 0 instead of 1, 2, and the threshold telling us the probability of a 0, 1 instead of 2. Question?
Oh, no,
Yeah.
no, sorry.
Okay, you had like a look that you were going to
Oh.
ask something maybe.
Yeah, I was probably just thinking.
Probably just thinking. Yeah, that's okay. Thinking is encouraged.
Can you repeat what you said about the threshold for like the Ys and stuff?
Yes. So, general terms. An intercept tells you the probability of the higher category instead of the lower. A threshold tells you the probability of the lower instead of the higher. So, an intercept tells you the blue, a threshold tells you the red. -1 gets you back and forth, because logits are symmetric.
If you multiply it by -1, you mean?
Yep. So these numbers, let me see if I can get them on the same page. Nope. -0.2 is the intercept. 0.2 is the threshold. Intercept times -1 is threshold and vice versa. So intercepts tell you the probability of the higher, thresholds tell you the probability of the lower. Now what the hell that is depends on which submodel you're in. So the first submodel is the probability of 0 or 1 or 2 as the higher versus lower. The second is 0, 1 versus 2. Okay, 2 questions. You first.
You just have to know that based on the package that you're using, what it spits out.
Yes, because they're not labeled well. In SAS, for instance, it defaults to giving you thresholds and it labels them as intercepts. I shit you not, it does. You just have to know. But this is how you know, is if you can come up with your answer key table and reconstruct what probabilities are being added together, then you can figure out if you're in thresholds or intercepts. Okay, question.
Is it probabilities or logits?
So the model
The
is,
-1 and the 1.
these are logits.
Yeah.
Yes, thank you for the clarification. I'm trying to shortcut the words, and I shouldn't be. This is the logit of the probability of an answer greater than 0. This is the logit of the probability of an answer greater than 1. Yeah. Yeah, I'm getting sloppy.
So it's all still logits.
The model is always in logits. The model, everything is in logits. But margins, and in SAS, it's the prediction package, or not SAS, in R, it's the prediction package. They are going to take you back from logits into probabilities. And the reason that it's cool to do it with these coefficients is because these are not slopes. These are predicted outcomes. Intercepts are predicted outcomes. They're naive predicted outcomes that are assumed to hold for everybody in this model, but they will become predicted outcomes for people whose predictor values are 0. They're still predicted outcomes. So we can go from logits, we're going to skip over odds today because this is hard enough, and we can go back into probability. Okay, did you get everything? We get everything put together? Maybe? Yeah. So I'm going to tell you right now in your homework, I'm going to ask you questions, and you're going to have to figure out if I'm asking for the threshold or the intercept. I am going to do that to you, because I want you to think about the conversion of the two, and the fact that you can get them both out of the same model if you can multiply one of them by -1. So cut in Stata, these are thresholds. This is the logit of the probability of the lower category instead of the upper. Okay, so from this point forward, thresholds are gone. Just wave goodbye. We're going to predict the higher score, just like every other linear model on Earth. In R, welcome to VGLM. I have no idea what the V stands for. V does not factor into any of my acronyms for this. So this is the empty model for the 3-category outcome. That's my labeling system. The family is cumulative with another set of parentheses. So parentheses in R are everything. Link equals logit link. Reverse equals true, and parallel equals true. So these are the magic options that differentiate this function from everything else that I could find, is that you have both choices. Reverse equals true means change it from thresholds to intercepts. Parallel equals true means fit the proportional odds, parallel slopes, force them all to be the same across submodels for now. But can you guess how I would change this to allow different slopes? What's the opposite of true? False, yeah. So that part makes sense. So for now, we don't have any slopes, so this is irrelevant, but these are what those choices mean. I'm going to keep them in there for continuity. The formula then gives me the actual model. So it's just apply 3 as our outcome variable, squiggle 1. So you're not listing things separately by submodels yet. And then I ask for the summary, and here's what I get. Okay. So coefficients. Intercept, off to a good start. This is in fact an intercept. Here's the -0.2, which is the logit of the probability of an answer greater than 0. Intercept 2, okay, it's just listing them in order. I can live with that. Is the logit of the probability of an answer greater than 1. Cool. Then it gets down here and it tries to help me. Name of linear predictors. Logit link probability greater than 2 or greater than 3. And I have a note here, no. What is my scale again? What are my choices? 0, 1, 2. So could this possibly be the probability greater than 3? No. I don't know why it does this. So just ignore this. Unfortunately, we have to stick with the 1, 2 instead of the 0, 1 because there's no choice. So in Stata, it's based on your actual numbers, like at 0, 1, 2, so it starts at 0. R is just listing them in order, so it's starting at 1. So the onus really is on us to figure out what each submodel is because the labeling systems may be inconsistent and or wrong. So are you feeling better that this was difficult to figure out on your own?
Yeah.
Yeah, it is
I'm
difficult.
starting to understand things that I had no idea how to interpret before. Like
Yeah.
I didn't know that the cut was the threshold, but now
Cut
I
is the
know, and I'm
yep.
glad I went with the go logit too instead of the o logit, or everything would have been wrong.
That's
Like,
right.
I would have been interpreting
Well, no, not
in a certain
necessarily.
sense, like, but the way that I was talking about it, like I was talking about it, the cut, like it was an intercept,
Mhm.
and so like that would have been
So,
pretty bad.
so here's the fun part. In OLogit, it does give you the cuts, but the slopes go the other way. Seriously, the slopes still predict the higher category, even though you have a threshold giving you the lower as the baseline.
Huh.
Yeah,
That's weird.
it is weird. That's very common, unfortunately, that there's two different directions of the model happening in the same time. Yeah, I can't handle that. So that we're going to have intercepts and slopes. Same linear predictor that we're all used to. In this package, it gives you something called residual deviance, which is the -2 log likelihood directly, so you don't have to do anything to ask for that. And then it gives you the log likelihood. So log likelihood -370 times -2 is where the 741 comes from. So those are telling you the same thing in different metrics. Remember, in log likelihood, that smaller is better. Think of log likelihood. Log likelihood is height. -2 times the log likelihood is shortness. Better height or less shortness, telling you the same thing. Here's AIC and BIC for comparison. We would use those to also look at changes in the model as we add stuff. And then I did the conversion into probability myself to get the predicted probabilities that are consistent with those logits, and there they are in GENT. So 0.55 is the probability of answering above 0. 0.9, hang on. No, it's backwards somehow. Goodness gracious. 0.9 is the probability of the lower two in this case. I don't know how it did that, but it reversed it on me. The rest of them, though, should work. Okay. 255. We're hanging in there. Okay, let's put some stuff in our model, because no one fits an empty model on purpose once they figure out how to use their package. So I'm going to add my 3 predictors. There are no interactions in this whole example, because this was enough. Does that seem fair? I think it's fair. So these are just regular slopes, nothing fancy. So I've got beta 1 as the slope of GPA, beta 2 is the slope of graduate degree, beta 3 is the slope of public versus private. And note the notation. Beta 1 shows up in both submodels, beta 2, beta 3. That notation is meant to convey this idea of what's known as proportional odds, meaning that the models differ only in their intercept. Otherwise, we'd come to the same conclusions about the slopes, and indeed they are forced to be the same. So the PL option within GoLogit 2 says make this a proportional odds model. Cool, I can do that. Likelihood ratio test is the first thing we note. So that is a test statistic comparing the fit of our model against an empty model. The 3 in parentheses are my 3 slopes. So p-value says, yep, they help. So we have a significant prediction. If we drill down into the coefficients, so constant in Stata is last. These are intercepts. Who's feeling brave? The constant for the first submodel is -0.4 in logits. What does that number mean? In Zoomers, you can play along too. It's an intercept. It's in logits. I'll give you the hints.
That is the logit of the probability of selecting a 1 or a 2.
Yes, the logit of the probability of answering 1 or 2.
Yes.
So far, so good.
For someone with his GPA of 3, with parents as graduate degree and private school.
So yes, for someone with a 0 on my predictors.
0, yes.
Yep, because the rules about intercepts still apply. Someone with a GPA of 3 whose parents didn't go to grad school, who went to public college.
Okay.
Yep. So that part is still the same. The intercept is the predicted outcome when your predictors are 0 But what predicted outcome is the part we have to figure out. So this is the logit, the probability of answering 1 or 2 instead of 0, the upper instead of the lower. That logit is minus 0.4, which means less than a probability of 0.5. Beyond that, I don't know, without getting my calculator out. Okay, someone else want to try the other one? That logit is minus 2.5. Go for it.
Logit of the probability of -2.5 of greater than 1,
Yes.
for somebody with a GPA of 3 whose parents did not go, and what's the public?
Yes, the logit of the probability of greater than 1, so answering 2 instead of 0, 1, for somebody with a GPA of 3 and zeros on the other predictors. Yes, we've got it. And that logit is very small. So that logit to me looks like a probability of probably around 0.05, something like that. I could reverse translate it, e to the logit over 1 plus e to the logit. That's the inverse link to figure out exactly what the probability is. And I'm wondering if I dropped a minus sign. No? Okay, I'll have to troubleshoot this, why this is backwards later on, but maybe that was why. Nope, that's not it. Okay. So, good so far? Question?
Yeah, I think I'm still kind of confused as to why, like, so 0 in this case is greater than answering 2
In this submodel, the second one?
in the first
In
one.
the first submodel. The first submodel is dividing 0 versus 1 and 2.
Okay,
So this is the logit of answering higher, meaning
Oh.
1 or 2,
okay.
instead of 0.
Oh, okay, I see. And then 1 is answering 0.
No, 1 is answering 2, the higher
Okay.
category, because these are intercepts.
Ah.
Yeah, we're done with thresholds.
Okay.
We're done. I hate them, we're done. So the fact, you can tell that because it's labeled as constant on here, so it's trying to help you figure that out. So these labels of the submodels, you can think of this as like what the lower category is in each of these choices. So the first submodel is something greater than 0, this is something greater than 1.
Okay.
And it does directly correspond to how your data are labeled.
Okay.
So if you had a labeling system of 1, 2, 3, then this would be 1 and 2 instead of 0 and 1.
Okay. That makes sense.
Yeah, and R doesn't care what your labeling system is. Stata does, though. It obeys that. Okay. How about this number? This is 0.6. It is the slope of GPA. It is statistically significant, and it is positive. Who's feeling brave?
I have a question first.
Okay. Then you can feel brave. Maybe.
With these, if
Mhm.
it's less than 1, that means that the slope is actually negative, right?
No, these are in logits.
These are logits.
Yep, these are not
the
odds. You're
ratio.
thinking of
That's
odds.
what I'm
Yep.
thinking of. Okay.
And I know that because in the
It says
command,
coefficient for 1.
yeah, there's no OR that would turn these into odds ratios, and it's coefficient here.
Yeah,
Later on the page, I added OR, and then I turned these into odds ratios. So that's what you were thinking of as odds ratios.
okay.
Yep, so this is in logits. It's a positive number, that means it's a positive slope. 0.6, we'll just put that in there. What does it mean? It's a slope. Start off with for every.
As GPA increases by 1 unit.
Correct.
The log of the logits
The logit.
of applying, of being, of being at or very likely to apply for grad school increases by that, because it's the same across both of them. right?
Yes, so 0.6 is the expected change in the logit of being a 1 or a 2 instead of a 0. But it's also the expected change of being a 2 instead of a 0 or a 1. This is the same number here because the model is forcing them to be the same. So what we would say is the probability goes up if you have a higher GPA. The probability of what? Yeah, the probability. The end. Yes, it goes up. What does? It. So the GoLogit package, GoLogit 2, excuse me, I don't want to offend the people who made this in case 1 was shitty. 2 is clearly much better. It's writing this out on purpose to make you think about the fact that you are making these numbers the same. Like, this is a choice. Most other packages don't write them out separately. Like when we get to the R output, it just gives you the one number. But the interpretation is the same. This is the slope of GPA. For which submodel? Yes. Both of them. So it's positive. That means you're more likely to be in the higher category. Just doesn't care which category you're talking about. Likewise, the other two slopes are positive. Parent graduate degree more so. People whose parents went to grad school are more likely to be in the higher category. The logit of answering 1 or 2 instead of 0 goes up by 1 if your parents went to grad school. The logit of answering 2 instead of 0 or 1 goes up by 1 if your parents went to grad school. And if you went to private school, who cares? Logit goes up non-significantly. So I'm trying to help out here by labeling these things. And any term that has 2 numbers in it is different across submodels, and any term that has 1 number in it is constrained equal across submodels. The analog to this, by the way, for those of you in the IRT world, the factor loading, or the A discrimination parameter, is the same across submodels in the graded response model. That is also a proportional odds constraint. Same exact thing. Here's the odds ratios. So if you want to provide effect sizes, and yes, you should know how to do this because the rest of the world uses them, who is not me. This effect size is positive. Does that mean that there's a positive slope in odds ratios?
Yeah.
Just the fact that it's positive?
Not necessarily.
Everything is positive. Odds are always greater than 0. What does a 0 slope correspond to in odds ratios? 1. Yeah. So the fact that this is greater than 1 means it's a positive slope. These are all positive slopes because I coded the variables to make it that way.
Well, with odds ratio, it's more like if it's higher than 1 or like higher than 0, like if you're comparing like something that's higher than 0 but less than 1.
Yes.
But like something that's higher than 1. Like that's more positive. Is that right?
So 1 to infinity is where positive slopes live, and 0 to 1 is where negative slopes live, and nothing is below 0. And my problem with it is numerically the negative slopes all look like they're more similar because they don't get to go to infinity the way the positive slopes do. That's my problem with it. I feel like it's a weirdly non-intuitive thing. But anyway, I don't need to belabor that point. So this is what's known as a proportional odds model. It constrains the slopes to be the same across all your submodels, even though the intercepts start you off at a different point. You want to see the R one? I think that'll be about all we have time for today. So we have the same options. Cumulative logit link reverse is true, parallel is true. The formula then is right there. Looks exactly the same as any linear model would. Coefficients, intercept 1 and 2. So the minus 0.4 and the minus 2.5 correspond to those two submodels. So they're in the same order at least, even if the labels are a little bit different. And then the 3 slopes are listed without reference to the fact that they're constrained. So they're just giving you the slope. So when you had to do this, did you do proportional odds models like this, where there's only one slope?
I did partial proportional
Oh,
odds.
up the ante for partial proportional odds. That's coming next. But that's probably coming next week. if I'm being real. So I have, let's see, one slope that's traditionally significant, two slopes that are, and then one that's not. In R, I have to do the likelihood ratio test against the empty model myself if I want some kind of is my model significant global statement. So I have, let's see here. Oh, it gives you exponentiated coefficients as your label. What would normal people call that? I'm going off the labels of the R output for the same model here. Exponentiated coefficients, what are those?
Odds.
Those are your odds ratios. E to the slope. Can I turn those into probabilities? No, because they're slopes. I can only turn predicted outcomes into probabilities. So yes, that's where your odds ratios are. I will also ask for those because they do show up by default. Here is my call to ANOVA to do the likelihood ratio test. It looks a little different than it did before. So I had previously not shown in this handout actually no, I did do it this time. Sorry, I forgot. I did the empty model. That way we could figure out what the hell we were looking at. So that is the nested model relative to my 3PO, which stands for proportional odds. And then it didn't work at first, and so I went into the documentation and tried to figure out why, and I come up with this. I need to add type equals 1. I don't know what that means, but it didn't work without it. So this is the ANODA instead of ANOVA output, analysis of deviance table. But it's doing the difference in -2 log likelihood, which is 24. 3 slopes is how many different parameters we have relative to the empty model, and there's the p-value that goes with that, treating it as a chi-square. So yes, same conclusion as Stata. This 24 likelihood ratio test statistic with the p-value is exactly what we see right here for you. So it's doing it for you. So anytime you have a comparison against an empty model, Stata will do that likelihood ratio test for you. But if you want to compare alternative models that you fit, you have to do that yourself with the LR test function. Okay. Because some people don't just want odds ratios, they want confidence intervals of your odds ratios. Yeah, it's a thing. I know. I figured out how to do that too. So you can give them a point estimate for your odds ratio, and you can also give them the precision around it. And what would control how wide these intervals are? One thing, in these models at least. How wide they are. Like, why would this be important to know? What controls the width of a regular confidence interval? Standard error. What controls the size of a standard error, besides the strength of the slope and the scale? Say it? Alpha level? Yes, but I'm going with a 95% confidence interval here. How do you make your interval smaller? It's simpler than that. Sample size, that's it. Yeah, the fewer people you have, the wider these things are going to be. The more you would expect a different answer across samples from the same population, the smaller the sample is. So this conveys the uncertainty around your slope in the odds ratio metric, the same way that you could convey the uncertainty around it in the logit metric, but nobody knows what a logit is, so that's probably not going to help them. But you can think of these as equivalent to significance tests if you use the same confidence level as you did with your alpha. So for instance, the last one here, the effect of being in a private college has an odds ratio of 1.06. The fact that this confidence interval overlaps 1 makes it non-significant. In logits, if the confidence interval overlaps 0, it's non-significant. But in odds ratios, if it overlaps 1, it's non-significant. So you can choose to augment your effect size with a measure of variability around it. And there's various ways to do that as well. Okay. So then coming next week, the exciting conclusion of, are these slopes different across models or not? I know, you're going to be on the edge of your seat. You can't just binge watch the show and find out what's going to happen next. You got to wait. But I'm sure you can do it. Question?
One question, you just said logic is hard to interpret.
Yes.
But like.
Not to me, but to everyone else.
But how to interpret odds ratio? Why odds ratio is easy?
I am not the person to ask. I do not understand odds ratios. Because what you end up doing is multiplying not just the variable that it's for, but all the other variables. Like exponentiation is like a multiplication of everything together, and I can't handle that. It breaks my brain. So maybe someone else can tell you why they like odds ratios. But what I can tell you is that in these models, they are expected. Like you need to have a column at the end of your output that has it, or someone's going to yell at you.
It's kind of like, because nobody knows what a logit is, but we have a sense of what odds are. Like, and it makes it easier to talk about like the change. So like, can you scroll to the,
Odds ratios?
yeah.
Sure thing. Oh, let me go back to the model we were at. Here's some odds ratios. Okay.
So like, you can talk about like, as GPA increases, the odds of being in a higher level increase by 1.85.
But it's 1.85 times. Like it's not
Right,
it's
so,
not
like,
additive.
It is like a times effect,
Yeah.
but like that, for some reason, even though like you still don't know like times what exactly, like some people say that just the fact that it's not in a logit, that nobody has no idea what it means, the fact that it's an odds of something
Yeah.
makes it more tangible for interpreting.
On
But
yes.
it's certainly up for debate, like whether or not it does. Like interpreting these are always kind of weird.
Yeah, I found a website. It's on slide 20 of this lecture, and it's literally called FAQ, How Do I Interpret Odds Ratios? And it's a whole discussion about it that I found useful. But like the odds are 2.7 times higher per unit if like the odds ratio is that. It's a timesing that the timesing part is the part I can't handle, plus the fact that all the negative slopes are shoved between 0 and 1. I also can't handle that. So yes, I like logits, but the world wants odds ratios. But you know what? You make both columns, you keep everybody happy, right? It's not that hard. As long as your columns are clearly labeled, then you're good to go. Okay, thanks for being here. I will be around if anyone wants to ask last-minute questions. Otherwise, have good weekends. Let me know if you need help with homework, and I shall see everyone next week. Happy logiting.